Welcome back, ladies and gentlemen. Today we're going to tackle section 12.6, the volume and surface area of spheres. Up on the screen, as always, you'll see your exit question for the day. I'm going to start you off with a theorem. Your first theorem for the day basically is just a formula that tells you how to calculate the surface area of a sphere. I'm going to give this one to you and I'm going to show you how to get the volume of a sphere. But for now, you can assume that the surface area of a sphere is 4 pi r squared, which kind of coincidentally and interestingly is the area of 4 circles of the same radius. So it's 4 times the area of one of the circles of a cross section of a sphere. If you're curious why that is, you can go ahead and do a YouTube search right here for the surface area of a sphere proof. And the particular video that I like is Mathematics Online, and it uses a polygonal proof to show how the surface area of a sphere ends up being what it is. But for our purposes today, I'm going to tell you that it's that, and you're allowed to assume that. And I'm going to assume that as I describe to you how you go about figuring out what the volume of a sphere is. So let's say we want to find the volume of a sphere. How do we do that? It's got curvy things all over the place. It's just a curve. A sphere itself is just the collection of points that are equidistant from a point in space. So every bit of that surface is curved, and everything that we know how to find the volume of has polygon sides. So how do we do that? Well, we're going to consider a very narrow strip of a pyramid, like that. And you might say, well, that's not really a pyramid because that base is actually curved. And you're absolutely right. It is not a pyramid. It is a very close to pyramid because it has a slight little bubble on the end of it. But here's what we're going to do. In the big scope of this proof, we are eventually going to not just examine one of those pyramids, but a lot of them. And not only just a lot of them, but an infinite number of them. And if you can imagine cramming more and more pyramids and making them tinier and tinier and thinner, that this base would approach a shape that is flat on the bottom, if that makes any sense. It's also going to approach an area of 0, which is kind of trippy, but the math is sound and that's how we do it. So to get started on this one, let's take a look at that one pyramid that we're looking at and try to find the volume of it. As you recall, the volume for a pyramid is 1/3 times the area of its base times how tall it is, which I don't know what the area of that base is, but I'm going to name it B1, the base of pyramid 1. And I would really like to know how tall it is so I don't have to keep guessing. So I'm going to say that it's R, standing for the radius of the circle or the sphere. And you might argue with me again that says, well, that is not how tall the pyramid is. Radius is actually this segment right here, each of these 4 segments, which isn't even a slant length. But again, I'll argue back that once we allow an infinite number of pyramids and this surface area to approach 0, all these edges of the pyramid are going to converge on each other, and once that surface area is 0, this pyramid will be R units tall. Crazy, huh? Well, that's one of them, and if we plug radius in for the height and B1 in for the area of the base, we get that expression. But that's only one pyramid, and we need lots of them. So imagine splitting up a sphere into a whole bunch of these pyramids and adding them together. So we're going to take the volume of a whole bunch of them. We'll name each base for the number pyramid that it is, and we'll add them all together. So that's the volume of a pyramid, that's a volume of a pyramid, that's a volume of a pyramid. And we do that forever until we're done with all of our pyramids, which in this case would be n of them. So that ... goes on for a long, long time. But if you can handle that, take a look here. We got a factor of 1/3 and R in every single term. So what I'm going to do is I'm going to undistribute or factor out that 1/3 and that R to the outside. And then I'm left with B1 plus B2 plus B3 plus on and on and on until I add the area of my very final pyramid. And this expression right here means something to us. Okay, so if we add up all the areas of all the little pyramids all over the sphere, imagine there's like an infinite number of them, but if you add all those little areas up, what do you end up with? Well, you end up with the surface area of the sphere, which is 4 pi r squared. So we can substitute in for that giant expression those four little characters right there, 4 pi r squared. And from there, it's just a little bit of multiplying together 1/3 times 4 and radius times radius squared to get 4/3 pi r cubed. And that is your next theorem and your final theorem for the day. The volume of a sphere is 4/3 pi r cubed. And in dealing with this formula, just a little heads up, you're going to have to deal with fractions, pi, and cubing a number, all things which you don't do on a daily basis up until this point in math. So I'm going to do a few examples here that are going to help you figure out how to treat each one of those situations. So, first example. Find the exact volume and surface area of the solid. See if you can pause the video and come up with a game plan on how you would do that. I'm going to take care of volume first. You could do either one, doesn't matter. But here's my game plan for finding the volume of this shape. And I should maybe explain what this shape is. This is a cylinder with a flat base, and then the top of it has been scooped out, so there's kind of a negative volume here. It's been scooped out of a hemisphere. So what I'm going to do to find the volume of it is I'm going to find the volume of the cylinder and then subtract the volume of 1/2 of a sphere with that radius. So from there, I'm going to plug in the general formulas that I know for the volume of a cylinder, which is pi r squared times height, and then my half of a sphere. So I've introduced a factor of 1/2 times 4/3 pi r cubed. So that's the volume of the sphere. And then we can multiply stuff together and plug in numbers from the drawing. So we got 6 for a radius, 15 for a height. Here we do a little fraction multiplication. We get 4/6, and then we have 6 to the third. Now, you can do this 6 to the third with the caret key on your calculator, but check this out. You've got a 6 on the bottom, and you got 3 6s right here, so one of them cancels. So this is just like 6 squared. On the next line, you can multiply all those numbers together to get 540, and then that's 6 squared, which is 36, times 4. You can combine those numbers together to get 144. And then finally, since they both have a pi on them, they are like terms, so you can combine them into 396 pi inches cubed. Let's move on to surface area. See if you can come up with a game plan for surface area. Here's my plan. Even though this is a negative volume, it is positive surface area. Okay, so that confuses some people. Picture how much paint would you need to cover the side of this object. You would need to paint this surface right here, so it is positive surface area. Anyway, we have the base of the cylinder, which is a circle. We have the label of the cylinder, which is the circumference times the height. And then we have another hemisphere, half of a surface area of a sphere there. So jump right in, throw in all your general formulas. Pi r squared, 2 pi r h, that was from a chapter ago or a lesson ago. And then you've got 1/2, again, that factor because we're only dealing with half of a sphere, times 4 pi r squared this time. And we have all the numbers. We don't have to go outside and figure out anything else. We can just plop them right in. You've got 6 squared, multiply all the numbers together. Each term will have a pi in it. So this is again a situation where you can combine all like terms, and you get 288 pi inches squared. Next problem I have for you is you are given the volume of a sphere, which is 4.5 pi cubic meters, and you are asked to find the surface area. So right away I would throw down the two formulas that you know. 4/3 pi r cubed for volume and 4 pi r squared for surface area. Now you may notice in both of those equations, the thing that connects them both and the thing that describes a sphere is its radius, and there's only one dimension to a sphere, so we kind of got to go for that. So we're given a volume, so we're going to use this formula and we're going to plug in what we know. We know that the volume is 4.5 pi, and we know that the volume of a sphere is this. So we need to solve this equation for r. And there's kind of a funky looking equation compared to what stuff you're used to. So remember, if you're evaluating an expression, you're going to do the exponents pretty much first. So when you're solving an equation, you're going to save that pretty much for last. So what we're going to do is we're going to undo the multiplication first. So we have r times pi and r times 4/3. So we need to divide by pi, which is convenient because if we do that, pi's cancel out on both sides. And then we need to get rid of that 4/3. Remember, a handy way to do that is to multiply by the reciprocal. That way numerators and denominators cancel. Over here, maybe a little calculator work, or if you want to turn 4.5 into 9/2 and do a little fraction multiplication, either one is probably about the same difficulty. Either way, you get this expression at the end. 3.375 equals r to the third. And sometimes you can do this problem in your head, but it's pretty difficult to think of a number that if multiplied by itself 3 times, you get 3.375. So this is the point where it's handy to have the calculator do the work, and you have to undo a cube. And just like you can undo a square by taking a square root, you can undo a cube or a thing raised to the third power by doing a cube root. And all you have to do there is draw a little radical symbol again, but specify that you're taking a cube root here instead of a square root. In a normal radical, it's assumed to be a root of 2. In any higher power, you have to write it down. So if you want to take the 4th root, you have to write a little 4 here, a 5th root, a 5, and so on and so forth. But you may not know how to do that on your calculator. You need to evaluate that part on your calculator. So take a look at your calculator. There's a little second feature right above the caret key, and you want to type in something in your calculator that looks like this. I want to take the 3rd root of this number. So you enter what root you'd like to take, and then what you'd like to take the root of second. And once you do that, your calculator will think for a little while, and it'll spit out 1.5 in this case. And then we take our 1.5 and pop it into our surface area formula to finish it off. 1.5 squared times 4, 9 pi meters squared. There's your assignment. I'll see you next time.